These are the notes for linear and exponential equations. This is in chapter 5, and we're going to do two sections of Hawks. One will be linear, 5.2, and the other one will be exponential, 5.4. Let's get started. A linear equation, if you were to graph it, it would graph a line. So it would be a straight line, and it can be going up, or it could be going down. It could be a constant, so in other words, it could be horizontal. And so those are just examples of graphs of linear equations. We're not going to be graphing them much. The formula that we're going to use is y equals mx plus b. This is slope-intercept form. This is the linear formula that we're going to use for all of our problems. There are other formulas, but this is the one that we're going to use. B is your starting amount. It's also known as the y-intercept. So if you were to graph this equation would cross the y-axis at that point. B is the number at the back. Y equals mx plus b. So B is at the back, and B is your y-intercept. M is your rate of change. It's also known as slope. That's what we are most familiar with, is the slope. Slope is the rate of change. So B is our y-intercept. It's going to be at the back. And M is our slope. Now, one thing to note about slope, slope is the number in front of x. So you're going to have a number in front of x, and that is going to be your slope. So if you look up here, notice that M is in front of x. M is your slope. X is the number of times that something occurs. A linear equation can either be a growth function or a decay function. There are words that mean something is growing, something is increasing, something is getting bigger. Some of those words would be add, increase, what else? Grow. And then the opposite would be your decay words. So subtract, decrease, decline, maybe that word would be used, but you get the point. These growth words are positive words, mean something getting bigger, and these decay words would be meaning that the value is declining or getting smaller. So that is our linear information, okay? This is the side for linear equations. Let's jump over here to exponential equations because you're probably not as familiar with exponential equations. This is something you've probably had limited experience with. But there are two formulas for exponential equations, The first is y equals a times, and then I'm going to put this b in parentheses, close your parentheses, and raise it to the power of x. That's why these are called exponential equations, because x is a power. Notice over here for linear equations, y, m, x, and b are all on the same line. But if you come over here, x has been raised. X is an exponent, okay? This is why this is called an exponential equation, because x is in the exponent position. That's the difference, well, one of the differences. Okay, for this particular formula, A is our starting amount. Another way to write that is it is your initial value. So whatever you started with in the problem, that goes into the A position. B is your rate of change, and it's typically a multiplier. Now, I'm going to talk about some words when we get down to the bottom that mean growth and decay. But you're going to be multiplying for an exponential equation. Whereas if you look over here, these were addition or could be subtraction, depending on your words. Some growth words we have are triple. Oftentimes you'll hear something about tripling. Tripling means multiply by 3. Maybe you'll hear the word doubling. Double means multiply by 2. Those words would mean that things are getting bigger. These are positive words. Things are growing and getting larger. Now, the opposite is true if you're decaying. If you're cutting something in half, that means it's getting smaller. And so your multiplier would be 1/2. Or maybe you're cutting something by thirds. So if your word was thirds, your multiplier would be 1/3. These numbers mean that your situation is decaying. You're going to end up with a smaller answer than you started with. And those words are very, very important. These type of words let you know that it's an exponential equation. Notice I don't have the word add or subtract here. These are multiplication words. And then the second formula, okay, so here is formula number 1, and x is an exponent. Formula number 2, it's y equals a 1 plus r raised to the power of x. Now again, x is an exponent for both Formula 1 and Formula 2. X is up in the sky. That is very, very, very important. X is not on the line. When you put these in your calculator, you're going to have to practice making sure you know how to use your calculator and raise something to the power of x. Okay. Our starting amount, same thing we've had in all the other ones. Our starting amount is the initial value. So where did this situation, whatever mathematical problem you're given, where did it start? R, this is a little bit different. R is going to be a percentage. If you are given a problem with a percent, then you are going to use this formula. This is how you know to use this formula. If you are given a percentage, then bam, it is automatically this formula right here. Okay, I cannot stress that enough. If you are given this formula, then you are going to use a percentage. If you're given a percentage, you're going to use this formula. Now, the rate must be a decimal. So I'm going to write that down really small here. The rate has to be a decimal. We're going to be given a percent, but we're going to convert it to a decimal. And I'll show you how to do that later on. Growth words here, increase, grow, that might be a word that's used, but these words are going to mean add, okay, because things are going to be growing and getting bigger. And then some decay words might be decrease or decline, or I'm going to put decline because nothing else is coming to my mind right now, but any word that means something is getting smaller, okay? Now, this is very, very important. I cannot stress this enough. Let me change colors here. Let's see if I can get my pen to go maybe to blue. All right, if you are given a nope, it's still red. If you are given a percentage, then you're going to use this second formula. That is the only time that you use Formula 2. Only time you use Formula 2 is if you have a percent. Okay, let's look at a couple of examples. Number 1, Cindy works at a job that pays $21 per hour. Write a function that describes the amount of money she makes. Okay, well, I don't hear any multiplier words. I don't hear triple. I don't hear double. I don't hear half. I don't hear quarter. And I definitely don't have a percentage. So that leads me to believe that this is a linear equation. Y equals mx plus b. And that is correct. Okay, Cindy works a job that pays $21 per hour. Write a function that describes. Now, function is a fancy word for equation. So don't let that scare you. I'm going to show you 2 different ways to write the answer. M, let's look at our notes. M is the slope. It's the number in front, and it is the rate of change. Well, Cindy's pay changes depending on how many hours she works. And how much does it change? It changes $21. So M is her X in this particular problem. I'm sorry, M is 21. M is 21, sorry. And then we don't know X, so I put an X there. Now B is her starting pay, her initial pay, the initial amount that Cindy makes. Well, guess what? If Cindy doesn't work any hours, Cindy doesn't work any pay. So Cindy starts out with 0 here. And we would write Y equals 21x plus 0. Now let me show you a couple other ways to write that same function. You could simply write Y equals 21x. Okay, so you would not have to put the 0 because it doesn't change anything. You need to know that her initial value is 0. But this is function notation. You would just write f of x equals 21x. This is called function notation. Now, I want to expose you to that because you're going to have a couple labs coming up in the next 2 weeks that you will see that notation, and you also may see that on Hawks. But this is function notation, and it's nothing scary. It's just where they put an f of x instead of a y, sorry. So this would be function notation. And that's the formula. Y equals 21x, or you can say f of x equals 21x. Let's look at number 2. Growing linearly, the balance. Now this one's tricky because I hear the word linear, but then I'm actually given an exponential equation. The balance on your credit card triples from $600 to $1,800. Now triple is one of your key words. If you hear the word triple, then that probably means something. If the balance were growing according to the exponential function, okay, let me write down the exponential function. Notice that they've used f of x instead of y. That's okay. So you've got 600, 1 plus 0.13 raised to the x. There's your function. Where x is the number of months, what would the balance be after 9 months? Look, they've already given you the formula. All they're asking you to do is plug this into your calculator. Now, we need to talk about this because it is very, very specific in how you plug in this exponent to a calculator. Let's talk about PEMDAS. I don't think we've talked about PEMDAS in this class yet, but remember, please excuse my dear Aunt Sally. When you plug this into the calculator, you have to follow the PEMDAS rules. Now, I have a graphing calculator as well as one of the cheapy handhelds, and so you have to just play around with your calculator to see how your calculator requires you to put this in. But you need to follow the order of operations. So the first thing you're going to do is put this in. This is parentheses. So P comes first in PEMDAS. Second comes your exponent. So this is the second thing because exponents come second in PEMDAS. And then the third and final thing you're going to do is you're going to multiply by this 600 third. You have to follow the order of operations. Now, I'm going to use my graphing calculator today because that's what I have here at my desk. But you need to practice and make sure that you're getting the answers that I get. If you do not know how to raise an exponent to a power in your calculator, it's not the same as multiplying. You're actually raising it to a power of 9. And that's not the same as timesing by 9. Okay, it says round your answer to the nearest cent because we're talking about money. So I'm getting $1,802, and that will round to 43 cents. It is not 42. This is the exact answer. $1,802.43. Nothing else will work. If you have 42 cents, that's wrong. If you have 44 cents, that's wrong. $1,802.43. Please practice with whatever calculator you're using and make sure that you know how to raise this to the 9th power. So again, the first thing you do is parentheses. The second thing you do is exponents. And the third and final thing are these multiply by 600. Okay? Let's do the last one. Assume your salary is $22,000 per year and $900 for each computer you sell. Write a function that represents your total pay. Well, this was kind of tricky because I don't really hear a specific giveaway whether or not it's linear or exponential, but let's look more closely. I don't hear a multiplier. I don't hear third. I don't hear cubed. I don't hear triple. I don't hear half. And I think about it and I'm like, okay, well, your salary is going up $90 for every computer you sell. So all things considered, I'm thinking this is a linear equation, and it is y equals mx plus b. B is your initial value. So you get a salary of $2,200. It's positive because it's a positive salary. Whether you sell any computers or not, you're going to take home $22,000, sorry. But what does change is your rate of pay based on the number of computers you sell. You're going to get $90 per computer, and here X would be the number of computers. So your initial, this is your answer, 90 is your initial value, and 22,000 is your starting point. Now, if you wanted to write it in function notation, again, you could just put f of x equals 90x plus 22,000. And you do need to know that this function notation is the same as the linear slope-intercept form. Okay, so join me for part 2 of this video.